We've already discussed the second order linear differential equations, their general solution and the existence and uniqueness of their solutions. So now we shall extend the theory further to discuss the general nth order linear differential equation. So we start by defining a general nth order linear differential equation. It is basically of the form P naught x yn. Here yn is the nth derivative of y, plus P1x yn minus 1. Here yn minus 1 is the n minus 1th derivative of y, plus up till Pn minus 1x y dash plus Pny is equal to fx. So unless it is stated, we have to assume that these coefficient functions, that is p0, p1 up till pn, these are continuous, and also the function on the RHS, that is fx, is also continuous on some open interval I where we wish to solve the equation. So now if we assume further that the p0 x, the coefficient of nth derivative of y, it is non-vanishing at each point of I. Similarly, we assumed in the second order equation, right? So if we make this assumption, then we can divide each term of the equation 1 by p0 x, and we get another equation in which the leading coefficient, that is the coefficient of the nth derivative of y, is 1. Okay, so we get the equation yn plus p1x yn minus 1 plus pn minus 1x y dash plus pny is equal to fx, and the associated homogeneous equation is given by just taking the 0 on the RHS. So here, if fx vanishes for all points in I, we get the associated homogeneous equation. Now we shall see some of the results that we did for second order linear equations, and we shall generalize for the nth order. So the theorem 1 is the principle of superposition for homogeneous equations. So it says that if y1, y2 till yn are n solutions of the homogeneous linear equation given by yn plus p1x yn minus 1 plus up till pn minus 1x y dash plus pny x pnxy is equal to 0 on the interval I, and if c1, c2, cn are constants, then the linear combination of y1, y2 till yn, that is the linear combination, is denoted by y, and it is equal to c1 y1 plus c2 y2 plus up till cn yn. This is a solution of the equation 1 on I. So basically, what is yx? Yx is nothing but c1 y1x plus c2 y2x plus up till cn yn x. So the proof can be done similarly as we have done for second order. We can just take the derivatives of y till nth order and substitute in the equation 1, and we shall get 0 because y1, y2, yn all satisfy equation 1. So we can combine the terms and get 0, and hence we shall get that y is a solution of equation 1 on I. Let's consider an example. So we consider the differential equation y triple dash plus 3y double dash plus 4y dash plus 12y is equal to 0. Now consider a function y1x. So this is what? This is a third order linear homogeneous differential equation. अच्छा, ये लीनियर क्यों है? क्योंकि लीनियर इक्वेशन का मतलब है y और y के जो डेरिवेटिव्स हैं, ये इनके लीनियर टर्म्स अपीयर करने चाहिए. मतलब इनका पार जो होगा ये फर्स्ट पार में अपीयर करने चाहिए. इनका पार अगर सेकेंड या ग्रेटर देन इक्वल टू 2, अगर कोई भी टर्म ऐसा अपीयर करता है, सपोज अगर यहाँ पे 2 होता तो ये लीनियर नहीं होता. ठीक है, तो हम लीनियर होने के लिए सारे y और y के जितने भी डेरिवेटिव्स हैं वो सारे पार 1 में होने चाहिए, प्लस इनके प्रोडक्ट टर्म्स नहीं अपीयर करने चाहिए. तो यहाँ पे सारे 1 पार के टर्म्स हैं डेरिवेटिव्स के, तो दिस इज अ लीनियर इक्वेशन. नाउ कंसिडर द फंक्शन y1x is equal to e to the power minus 3x. So now y1 dash x is equal to minus 3 e to the power minus 3x, y1 double dash is equal to 9 e to the power minus 3x, and y1 triple dash x is equal to minus 27 e to the power minus 3x. अब इसमें सब्स्टिट्यूट करते हैं इक्वेशन में, ठीक है, तो इसको इक्वेशन 1 बोल देते हैं. लेट इज सब्स्टिट्यूट y1 ट्रिपल डैश, y1 डबल डैश एंड y1 डैश. तो हमें क्या मिलेगा, माइनस 27 ई टू द पावर माइनस 3x प्लस 3 टाइम्स y डबल डैश. सो y डबल डैश इज 9, 9 3s are 27, so we directly write 27 e to the power minus 3x plus 4y dash. So 4 into 3 is 12, so minus 12 e to the power minus 3x plus 12y, so 12y1, so 12 e to the power minus 3x. ये क्या हुआ, this is equal to 0, so this is the solution of the equation. Similarly you can check that y2x is equal to cos 2x and y3x is equal to sin 2x, sin 2x. These are also solutions of this equation. So we have got 3 solutions of this equation. So by theorem 1 we get, and these are the solutions of all r, so for all x in r. So by theorem 1 what do we get? We get that if I consider yx is equal to c1 y1x plus c2 y2x plus c3 y3x, this is equal to c1 e to the power minus 3x plus c2 cos 2x plus c3 sin 3x. Then for here c1 c2 c3 are arbitrary constants. So by theorem 1 we get that yx is a solution of equation 1. Parallel to what we have seen for second order linear differential equations, we have the result for existence and uniqueness of solution for linear equations of nth order. So the theorem says that if we have functions p1, p2 up till pn and f which are continuous on the open interval I, okay, so these functions are continuous on open interval I which contains a point A, and we are given n numbers b0, b1 till bn minus 1, then the nth order linear differential equation yn plus p1x yn minus 1 plus pn minus 1x y dash plus pnx y is equal to fx. So here these yn, these are the nth order, so yn is the nth order derivative of y, yn minus 1 is the n minus 1th order derivative of y, that is yn is equal to dny over dxn. Okay, similarly yn minus 1 is equal to dn minus 1 y over dxn minus 1. So the theorem says that this equation has a unique solution on the entire interval I which satisfies n initial conditions. Ya is equal to b0, y dash is equal to b1 until yn minus 1 is equal to bn minus 1. So basically this theorem says that the initial value problem that consists of this equation, so the equation 1, let's say, okay, so 1 along with the initial conditions, these are the initial conditions. So the theorem says that these consist of these together make the initial value problem. So according to the theorem this initial value problem has a unique solution on the interval I where the coefficient functions and the function on the right hand side, that is fx, are continuous. Let us revisit the example in which we consider the differential equation y triple dash plus 3y double dash plus 4y dash plus 12y is equal to 0. So we saw that If we consider a function of the form c1 e to the power minus 3x plus c2 cos 2x plus c3 sin 2x, then this was a solution of the equation say 1 for any arbitrary constant c1, c2 and c3. Okay, so let us take the values for c1, c2 and c3. So let c1 is equal to minus 3, c2 is equal to 3 and c3 is equal to minus 2. Then our solution, let us call it yx. It becomes equal to minus 3 e to the power minus 3x plus 3 cos 2x minus 2 sin 2x. So then yx is a solution for equation 1, right? So let us see the conditions that y satisfies at x is equal to 0. Okay, so let us calculate y dash x and y double dash x as well. So y dash x is equal to 9 e to the power minus 3x minus 6 sin 2x and minus 4 cos 2x, and y double dash x is equal to minus 27 e to the power minus 3x minus 12 cos 2x and plus 8 sin 2x. So if you calculate y x at x is equal to 0, y dash x at x is equal to 0 and y double dash 0, then you will get y0 is equal to 0 and y dash 0 is equal to 5 and y double dash 0 is equal to minus 39. So by the previous theorem we can conclude that the solution, there is no other solution that satisfies these initial conditions other than this solution yx. Okay, so there does not exist any other solution different from yx with the initial values given by a. Let's call this as a, and hence now we shall see some of the concepts that we have already seen for second order differential equations, like linear dependence and independence, in the next videos.